Good day, everyone. Today I'm going to be talking about mineralogy for DMS. What is the benefit? Topics I'd like to cover are understanding the minerals in the DMS feed, looking at composition, liberation, shape, and porosity, looking at the washability analysis, and then I'd like to give a modeling example of how when you change liberation, you can also change the DMS performance. The type of mineralogy we're going to be using is called process mineralogy, as opposed to things like crystallography. So the objective of using process mineralogy is to find those factors that may influence beneficiation. And these are things like particle size, grain size, mineral associations, which is related to liberation, porosity, which would then change the density of the particle, mineral surfaces, so that's things like if you have clay covering the surface of the particle, particle shape and textures like roughness or smoothness of the particle. What's very important is also to look at things like the impurities inside the minerals. Those could be things like solid state inclusions or little tiny particles that are so small that become part of the particle and change its grade. And then lastly, looking at what weathering can do. Can weathering alter the properties of your minerals? So at the front end starting, we would look at mineral identification. And there's various ways of doing that. You can ask the mineralogist or the geologist. The different techniques that you could use could be things like X-ray diffraction, Fourier transform, infrared analysis, AutoSem, etc. And those will give you the list of all the minerals that are present in your sample. But more than that, you need to look at the chemistry of those minerals. As we said, is there elemental substitution? Are there other minerals that are so small that are micro inclusions? And the way to do that is to use the microprobe. The picture on the right, each color is a different mineral, and each number is a little spot on that mineral that's been assayed by the microprobe to get the inherent grade of a clean piece of that mineral. So once you've done that, you should have a list of the minerals that make up your sample, and you'll have correct information regarding assay and regarding density. Okay, liberation is very important, and there's generally two kinds of liberation that we look at. The first is called grade liberation, and that's related to the percentage composition of that mineral. This is what's very important for DMS. Another kind of liberation will be the exposed surface, which is more important for techniques like flotation or leaching. In those three particles that you can see, all three of them have 80% mineral A, 20% mineral B. So from a percentage composition, they're exactly the same. They'll have the same density and same assay. But clearly they will leach quite differently. So it's important when you prepare the feed for DMS to make sure you maximize the liberation that reaches that plant. And that may mean you need to look at things like changing the type of crusher from, say, a cone crusher to an HPGR, for example. Okay, the washability analysis is vital to understand and predict the performance of a material through a DMS plant. It gives the density distribution of the ore. So the traditional way of doing that is through heavy liquids, which separates a sample in a fluid medium, which is the same as the process, which is good. Lower densities of heavy liquid are pure liquids, and higher densities use suspensions. You can put large masses, kilograms, into it and fractionate them, so your accuracy can be quite good. There is an issue, and I put it in inverted commas, with porosity. So if you've got little bubbles inside your particle, little porous parts where there's air, the density would change. And is it an issue? Well, that's going to happen in reality, so at least it can flag it for you. The problem with heavy liquids, of course, is that they're toxical chemicals, both for people and for the environment. So in many instances, heavy liquids has been replaced by a unit called a ROVAL. There you can see a picture on the top right. What this does is it has either 7 or 21 cameras, and as the particles fall through, you take pictures of the silhouettes of those particles, recreate the volume of the particle, you measure the mass of the particle, and you get its density. This technique also has an issue with porosity and can also have an issue with concave surfaces that don't make a silhouette. Its advantage, of course, is that it is completely safe. So if we take an example and we say, let's assume we have a deposit, and from that deposit, an iron ore deposit, we get 4 samples from of the deposit, and we know from the mineralogist that there are 5 basic minerals that are inside that ore body: hematite, goethite, quartz, kaolin, and muscovite. We crush it down to -25, we sieve it into 2 size classes, and we do heavy liquids. We assay each fraction for the major elements and for the minor elements. And we think, all right, we're going to cut this ore at a density of 3.6, and we do that for all of the 4 samples, and we find that the product, the sinks at 3.6, has quite different chemical analysis. And the question is why? When we treat this ore, we can't keep changing the density so much of our plant. What's happened? And the way to do that is to look at the sample using mineralogy. And here we're going to look at AutoSem and the microprobe. And what do we find? Well, we find instead of having 1 type of hematite, there's actually 4 types of hematite. On the top left here, you can see a very dense particle of hematite. So you can see there's very little inclusions in here, and the density of that particle will be high, and it'll be very close to pure hematite. On the top right, we find fine pores inside the hematite. So it's still chemically very clean, but its density is going to be lower because of the little bubbles of air. Okay, the last 2 types of hematite are shown here. On the left, there's the coarse porous hematite, where the pores are very much bigger and the density has dropped a lot. On the right-hand side, we can see solid hematite, but it has tiny inclusions of quartz. What this means is that no matter how well you process this material, you'll never get the high Fe grades, and it'll always bring SiO2 grade with it. You can use the same technique to analyze the gangue. So we know we have different types of gangue, but you can see from the picture on the right that the muscovite can be divided into 2 kinds of muscovite: that which is clean and that which has phosphorus minerals embedded in it. And whenever you get that kind of muscovite attached to your hematite, it's going to upset your product quality. So let's look back at the DMS feed, not under the microscope, but at larger particles, and say, okay, what have we got now? And you can see composite particles. And this will explain why, to some degree, why the different product qualities at a density of 3.6 are happening. You can see the particles, both of them, now at stone sizes, are mixtures of dense hematite, fine porous hematite, coarse porous hematite. And the DMS plant will treat that particle with its average properties. Okay, so let's have a look at modeling this type of scenario. We'll use the properties of those hematites and gangues as we've measured them. There are the 4 types of hematite, there's goethite, and then the 4 types of gangue minerals. They've each got a density, they've each got a chemistry. You can immediately see that the quartz-rich hematite there has got high silica value that's going to come through. And you can see that the very porous one has only a density of 4.6. So let's create a fictitious feed. What we're going to do is we're going to make up 100% feed using these ratios of minerals: 10% dense hematite, for example, 20% quartz hematite. And we will crush that material and make a feed. What we're going to model is screening that feed at 25 millimeters, 8 millimeters, and 1 millimeter. And we're going to treat the 25 by 8 in a coarse DMS and the 1 by 8 in a fines DMS. But what we're going to do, we're going to look at two different scenarios. Now, what these two tables show is under scenario A, all the relationships between dense hematite, for instance, and all the other minerals are given a value of 1. It's the default. That gives the normal association between each mineral, like dense hematite and goethite, has a base value of 1. Compared to scenario 2 or scenario B, where you can see these numbers have gone up to 5. So dense hematite will now have 5 times more association, more locking with the gangue minerals. So scenario A, scenario B, exactly the same size distribution, same head grade, same assay in every size class. The only thing that's changed is the state of liberation. If we then do heavy liquid separation on that, and we now model that, what type of density distributions do we get? So on the right-hand side, sorry, on the left-hand side, you've got the coarse DMS and the fines DMS for good liberation, which is liberation A. And on the other side, we've got the same, but for poor liberation, which is liberation B. If we're going to cut at a density of 3.6, we want to look on the chart here near 3.6 and see how much near density material there is. And immediately you can see between liberation A and liberation B, there's a lot more material sitting around 3.6 for the bad liberation. Same thing for the fines. They're inherently much better. They don't have so much near material because the liberation is better. But as you make scenario B, you can see there's more near density material. Looking at the DMS modeling results, what can we see? First of all, on the coarse DMS with good liberation, we're getting iron grades of over 63. On the same coarse DMS, but with poor liberation, you can see that the iron grade has dropped down to under 60. A similar thing can be seen on the fines DMS, but the effect is a little bit less because the fines were quite well liberated to start with. But you can see a drop from 64 to 62. One question can be asked, how would you improve the situation under scenario B? The first thing would be, can you crush better to create less locked material and less middlings? Or secondly, do you have to increase the density cut point to get back onto grade? Now, one advantage of looking at each mineral type and modeling it in this way is you can take a view and see what happened in the performance across the DMS mineral by mineral. Now, what this table is showing is that in scenario A, you can see you're recovering a good amount of the dense, clean, high-grade hematite. And in scenario B, remember we're cutting at exactly the same conditions, but because some of this dense hematite is locked with low-density minerals, it will be pulled across to floats. And the true is also in reverse for the gangue. If you look, the gangue mineral under good liberation, let's say we're recovering here 12% of the quartz, that's gone up to 27% recovery in the poor liberation. Now this just goes to show how important getting that liberation correct before DMS is. Otherwise, you ring fence the range of performance that you could get. So to conclude, we know there's natural variation across the deposit, and this can make changes in the mineral quality and mineral liberation. You can use techniques like autosemi microprobe to quantify these variations. We've seen traditional DMS, very, very useful, very, very powerful, but often nowadays being done by a process called Rovol. We made a fictitious DMS feed. We created 2 states of liberation where that was the only difference between the two. And we modeled that through Corson-Fine's DMS. And the results were showing us that poor liberation gives you more near density material and a low quality product. Lastly, if you use a multi-mineral modeling approach, you can actually look at each of the building blocks, each of those minerals, and find which is the one that's giving you the biggest problem. Where's the phosphorus assay coming from, for instance? So in conclusion, mineralogy can be very useful in understanding DMS performance. I'd just like to acknowledge Anglo American for allowing the presentation and Multotec for the mineralogy images. Thank you.